Hi, now welcome again. This is my video number 16. Number 16. So let me recall you a couple of things before we proceed further. First, we have let's say we have a vector, right, or curve, where we have a position vector somewhere there. So let's say this is our position vector RT. Okay, so from the given vector function R, or position vector R, we can find, given R T, a vector function, or a position vector, or position vector. Because R is you can consider as a position vector. So from the given vector function R, we can find what? We can find the unit tangent vector. Okay, we can find unit tangent vector. So basically the unit tangent T is given as R prime T over magnitude of RT. Okay, and we can also find the normal vector, unit normal. Unit normal. Yeah, unit normal is given as n prime T prime over magnitude of T. T prime of T over magnitude of T prime. Alright, all this function of T. This is also function of T. So this is a unit tangent. Unit tangent. This is a unit normal. Okay, and we can also find the binormal. Binormal is written as, or defined as T cross n. So we can find binormal, vector binormal T. This is T cross n. T cross n. So this is known as vector binormal. The magnitude of B is also 1. Magnitude of B, this is also 1. So it's a unit vector as well. Now if you look at this that diagram, simple diagram here, we have the position vector here, and then if you differentiate to find what is the unit tangent, unit tangent means is tangent to the curve with magnitude 1. So this is our T. Alright, and the differentiate T, we have a unit normal. So unit normal means normal to T. So we have that's the unit normal, and this is perpendicular to T. And also for the binormal T, you can use the right hand rule, T times n, T cross n. So T cross n, you have some vector points toward yourself. Then how can we write this thing? So let's say those vector, this is vector B. So this vector V perpendicular to n, and also perpendicular to T. So we have that vector. So that's our I will keep the position of T, the R and T and N and B. So that's the relation between all those things. Alright, so if you can imagine, you have, let's say you have a plane. Okay, I just want to think this way. You have a plane where T or those lines passing through that plane. So you have plane, something like, so you have a plane like that. You have a line or a curve, those curve, or the position vector, those, that's passing through those lines in such a way that the tangent at that point, if you plot this tangent at this point, so this tangent will be perpendicular to that plane. Yeah, those tangent perpendicular to that plane. That's one case. So can you imagine those things? You have a plane that T perpendicular to that plane. So what happened basically, the vector N and B lie on that plane. Okay, that's the first scenario. The second scenario you can think of, a plane where the vector T is on the plane. Vector T is on the plane. So what you can see is that the N is normal to the plane. Okay, consider those scenarios. So let me write that in word. So the plane determined by the plane determined by vector N and B at point P, on a curve C, say. Can you see this? I hope you can see that. Yeah. On a curve C, is called the normal plane of C, is called the normal plane of C at P, at point P, and it consists of a line that are orthogonal to the tangent of vector. Yeah. So it consists of all lines that are orthogonal to the tangent T, to the tangent vector T. Okay, so if you can imagine this, a plane determined by N and B. So if you look at N and B here, this N and B, and we have a tangent here. Imagine that for the first case here, or the first node here, you have a plane, okay, in such a way that those N and B lie on that plane. Okay, I put this way. This is the first case. We're gonna write. I can write here. Let's say this is the first case that I described here. This is the first case. We have vector N and B on the plane. So let's call this plane M, capital M, as a plane on B. Okay. So in this case, we have T basically normal to the plane, normal to the M. And if you have any line there, if you have line on the plane, on M, any line on M, if you have any line, so those lines were perpendicular to T. Yeah, consider any. If you consider any line L in M, so what we have, those line L perpendicular to T. Okay, I hope you can imagine those things. So we have a plane where N and binomial lie on the plane and T unit tangent perpendicular to that. So in this case, we call that plane as a normal plane. So this is we call, in this case we call M is the normal plane. Normal plane. Alright, so that's the first case. Second case, or second knots. Alright, this one is number 1, right? Okay, now I have number 2. I have number 2. The plane determined by T and N. So the plane determined by T and N is called osculating plane. Osculating, osculating, osculating plane at of C at point P. Oh, sorry. Okay. So for a plane curve, the osculating plane is the plane that contain the for a plane curve, the osculating plane is the plane that contain the curve. It's a plane. Osculating plane is the plane that contain the curve. Okay, so what is this? Now come back to the diagram here. Come back to this diagram. So now imagine that, or let me do it. So this is the first case. Okay, this is the first case. Now let me do it. The second one, I draw the other one. So let's say we have a curve, right? And we have a tangent T. This is the point P, and we have normal, and we have B. Let's say this is our B. So we have that, we have that, and we have that. So it's perpendicular. Okay, so imagine that we have a plane where those determined by T and N. In other words, T and N lie on the plane. So let's call those plane M. So T and N lie on this plane M, or let's call it M1. The previous one M, so let's call this one M1. So you have a plane here. So you have a plane. That's a plane. Yeah, in such a way that N and T lie on the plane. Okay, this is your R. This is your RT. And as you can see there, those curve, yeah, this curve, let's say this curve L. So L is on the plane. Okay, this curve L is on the plane together with N and B. So in this case we have the binomial vector is perpendicular to the M. In other words, the binomial vector is normal to the plane. Now in this case, if you can imagine that what is the osculating plane actually? Those plane where those curves are on the plane, so you can imagine that it's kind of if those plane keep on turning, it's just like what we call those in English pintalan. You know, in Malay we call it pintalan. Yeah. So it's going keep on doing that way. So this is what we call it osculating plane. So hopefully you can get those things. If you still have a problem, let me know. And then yeah, somehow we'll try to explain. I try to explain those things again. So that's the second case. The first case we have a normal plane. The second case we have the osculating plane. Yeah, we have osculating plane. The second case where the osculating plane, the n and n, a tangent and normal on the plane, and for the n binomial perpendicular or normal to the plane, M1 here. Whereas for the first case where normal and binomial on the plane, so in this case we have tangent is normal to the plane. Yeah. So okay, let's see some example on this plane. Example. Find the equation of normal plane. Find the equation of the normal plane and osculating plane of the curve, and osculating plane of the curve So the curve is given as RT as we have cos t, sin t, and t at point, let's say point P, given as 0, 1, pi over 2. Alright, so look at the solution. So we need to find, normal plane. To find normal plane, we need tangent, right? We need vector tangent. So vector tangent, in this case, tangent, let's call this plane M1, let's call this plane M2. I just want to give a name so that's easy for me to recall. Okay, so in this case, T is perpendicular to M1. Okay, and for the osculating plane here, B is normal to M2. Why do we need this normal? Because in order to find the equation of a plane, what we have seen this thing, equation of a plane, we need to find the at least we need a point on the plane and normal to the plane. So that's why we are looking for the normal and normal. Yeah. Let me recall those things. To find equation of a plane, you have a plane. In order to find the equation of this plane M, you need one point on M. Let's say P0, X0, Y0, Z0. Okay, and you need one normal to the plane. Those normal, let's say A, B, C, and then with that point and normal to the plane, we can find the equation of the plane. The equation of the plane is given as what? We have AX plus by plus cz, this is equal to ax naught plus by naught plus c z naught. Okay, let's do it this. So that's why in all these cases, to find normal plane, to find osculating plane, we need to find a vector that perpendicular to the plane. So in this case, a vector perpendicular to the normal plane is t, and vector to perpendicular to the osculating plane is b. So we need to find t and b. So let's do it. So so normal planes, to find t, we find t is r prime over magnitude of r prime. Okay, so r prime is just from there. So we have negative sin t, cos t, and 1. And then if we evaluate at point that this is for x, this is for y, this is for z, so we have z equal to t. So you can see z equal to t, so I can take t equal to pi over 2. So then I can evaluate those at t equal to pi over 2. So I can write like this to make it things clearer for you. Yeah, we evaluate r prime at t equal to pi over 2. Just substitute into that pi over 2. So that gives you minus 1, 0, and 1. Okay, so this vector actually act as a tangent to that, not unit tangent, but tangent to the plane. Yeah, if you want to find the unit tangent, of course it's easy for you to find that. Unit tangent is r prime over r prime, magnitude of those. So we have minus 1, 0, and 1 over magnitude of, so we have 1 squared plus 1 squared, so magnitude of 2. So that is the unit tangent of that. Okay, from here you can find, so therefore the equation of the plane, so therefore equation of normal plane at P, yeah, P is a point here given in the question, is given as, so we have normal, this is normal, so this is in terms of equation of plane here, in terms of equation here, the normal is given here, so this is A, this is B, this is C, and point x naught, y naught, z naught is given here. This is x naught, y naught, z naught. You need to find those things, x naught, y naught, z naught. Okay, so what we have from here, then from here we have this is unit tangent, so we have a x, so we have negative 1 over sec 2x plus we have 0 y plus 1 over sec 2 z. This is equal to on the right hand side we have ax naught negative sec 2, our x naught is 0, plus 0, our y naught is 1, and plus 1 over sec 2, our z naught is pi over 2. Simplify this, you get whatever it is. Yeah, you're supposed to get I have space, but I just need very small space here, so I write here. So you get z is equal to x plus pi over 2. I think you can simplify this. It's not difficult to show that. So you got those things, because this cert you can cancel out everywhere. What left is just the nominator of those things. Alright, so this is the equation of the tangent plane, normal plane, sorry. So now for the osculating plane, what we need is vector binormal, because for the osculating plane, vector binormal is normal to that plane. Yeah, for the osculating plane, we need B. Okay, now from the given T, we have R prime. This is negative sine T cos T and 1. Alright, and we have shown that R tangent is given as R prime over R, magnitude of R prime. That give you negative sine T cos T and 1 over Z2, because sine squared cos squared is 1 plus 1, so you got Z2. Then we need to find what n is. Alright, n is vector differentiate T, whereas then divide by magnitude of T prime. Okay, so what you have here, we have sine, so negative cos T, negative sine T, that's 0. Magnitude that you have 1. Okay, magnitude of those you have 1, and you have already square root that, so this is just divide by square root 2. Okay, and then you can find what B is, where B binomial is given as T cross n. Yeah, so your T is where is your T? This is T. Okay, so that your T. Let me write this thing. Yeah, this is, no, I'm sorry, this is T, not T prime. This is T. Yeah, that's correct. That's T. Now, so T times those things, so we have I can write that as negative sine T cos T and 1 cross n, negative cos T, negative sine T and 0. Divide by this one as square root 2, this one over Z2. So what you have here is 1 over, am I correct? I think correct there. T prime 1. Okay, so we should have those things. Okay, so you can do this thing. I just leave it that part to you, and hence we evaluate the B pi over 2, because our point P is pi over 2. We evaluate that point P pi over 2. This will got 1 over Z2, 0, and 1 over Z2, and therefore you can find the equation. So therefore, equation of the required equation, which is the equation of the osculating plane. So we have 1 over Z2, because we take out all those things, and here we have x minus x naught, which is our point is 0. Yeah, P is 0. Let me write P. Your P is 0.01 pi over 2. This is your P. Now x minus x naught plus y 0, y minus 1 plus 1 over Z2, then z minus pi over 2, that equal to 0. So this will give you z equal to x plus pi over 2. So this is the osculating equation of the osculating plane. Okay, Let me give you some exercise. Yeah, exercise. Number one, we have let's say RT is given as A cos t, A sin t, and BT. So find T, N, and B, and also find the normal and osculating plane. Normal and osculating plane. At say what? At point P. So in this case, I can have let's say A can have here A B. Okay. Now, cos pi over 2 is 0. So let's say okay. So let's say point P is 0. Then pi over 2 so you have 1. So we have B pi over 2. That point. Okay, so that's a point. So that's the first question. The second question is given RT as ET sin AT cos t, ET sin t, and ET find T and T, N, and B at T equal to 0 and T equal to pi over 2. And number 3, if xt equal to t and yt equal to t cube, find kappa curvature using n is 1 over magnitude of v dt over dt kappa. So you can find all these things. From there you can find what n is. Basically you can have your r, you can have the position vector for that. Then you can find what tangent, you can find what normal, then just plug in, then you can find what k is. Yeah, and compare your results with, if you use kappa using x dot y double dot minus x dot y double dot over x dot squared plus y dot squared 3 over 2. Okay, so that's the exercise for you, as just to find the normal and osculating plane. That's not really difficult actually. Right. Now let me discuss a little bit some of the example that related to, you can say, the application of the vector in general. Yeah. So example. Now consider this. Yeah. Consider, let's say we have a a cannon, you have a cannon, fired a cannonball, so the projectile is like that. So hit the ground, this is ground, so that's the final destination. Okay, with the inertial velocity V0, the angle of elevation alpha, and the external force is the gravity. We have the external force. So this is the distance. That's the distance. Okay. Of course, if you can consider this or imagine this the cannon, if you change alpha, the distance d also change. So somehow there must be a alpha that can give maximum distance. Okay, so let me write those in as try to summarize those as a problem. So a projectile is fired. So like a cannonball that we fired there. So angle of elevation, we have angle of elevation alpha, that, and we have initial velocity V0, external force which is gravity G. Okay, so the question is find RT, the position vector. What value of alpha that maximize the distance? So that's the problem. How can we find those things? So first thing we need to find R. So with all this, actually we can find what A is, we can find what V is, you can find, and later on we find R. So there's a solution, right? So we have the force, which is F, is MA, right? Everybody knows this thing, MA. Yeah, where your A is minus J. This is your A. The acceleration of those things. And Y negative because it's the opposite of Y axis. You know, it's to the negative of Y axis. So that's why we have negative. So if this is the case, then our F, so this is actually negative mg j. So we can find F is that, and of course the magnitude of G is magnitude of A, which is the gravity, right, meter per second. Now from A here, so we can find what the velocity, because we have A is actually V prime. Yeah, A is actually V prime. Yeah. So this is negative Gj. Alright, so we can find what V is from there. We just integrate that with respect to T. So we have negative GTJ plus another vector C, constant. Now to find C, we need the initial condition. What is the initial condition here? Initial condition here. Alright, initial velocity, given the initial velocity V0. So which means, okay, so I can say how to find the initial condition. So when T equal to 0, we have Vt is V0. Then this is the initial condition. Alright, so using that, I can find Vt. So therefore we have Vt, or just V0, I can say V0 is equal to, this is 0, so we have 0 there, so it's T. So therefore we have C equal to V0. So this is V0. This is equal to V0. Okay, so therefore our V T is negative GTJ plus V0. And we know that R prime is, V is R prime. V, this is R prime. So therefore we can find, you can find R. So RT, we integrate R prime, that gives us negative half G T squared J plus V0 T plus another constant vector, let's say D. And to find D, you can use another initial condition here. At this point here, let's come back here. At this point, R is 0. Yeah, at this point, T 0, R is 0. That's understood, right? So we have at T equal to 0, so we have R0, this is 0, this is 0, that give you D, and distance is 0. So therefore our RT is negative half G T squared J plus V0 T. Okay, so we solve the first part where we want to find R. Next, we need to find what is alpha that maximize the distance. So if we take the magnitude of V0, this is equal to V0 without the vector sign there, then we have the vector V0 is given as, so you can look at here. Yeah, if this magnitude here from here to there, the magnitude is given as V, not this magnitude of V, then you can find the element for X, you can find the element for Y. So in this case, that element for X is given as what? V0 cos alpha, and element for Y here you have Y V0 sin alpha. Okay, so just add up those things, then you can find what vector V is. So therefore we have, so V0 is given as, we have V0, this is for the X element, cos alpha I plus V0 sin alpha J. Okay, so if you substitute those V0, substitute this V0 into R, so what we have, so therefore our R T is, substitute this V0, this V0, this V0 into this R that we have obtained earlier. Okay, so we have RT is given as V0 cos alpha T I plus V0 sin alpha T minus GT squared j. Then from here we can find the parametric equation, which is our x is given as v0 cos alpha t, and we have y equal to v0 sin alpha t minus half g t squared. Okay, so if you want to find d, just come back here. If you want to find d, so what you can see, this d is on the x-axis, so which means our y is 0. Yeah, y is 0 on x-axis, y is 0. So therefore we have, yeah, to find d, so we have our y must be 0. So if y is 0, then you have from there v0 sin alpha minus half g t. You can take out 1t, that gives 0. So we have t equal to 0, and the other one is t equal to we have 2 v0 sin alpha over g. So which means, okay, the time when the ball of that cannon hit the ground, so when t equal to 0, which is at the beginning, and then when t equal to that number, when it's hit the ground here, so that's the time. Okay, and so therefore you can find d. Your d is actually x, so your x with t is given there. So where is our x is here, so we have v0 cos alpha, okay, and then t is this, so we have 2 v0 sin alpha over g. Okay, so just simplify this, so we have v0 squared over g, that you have 2 cos alpha sin alpha, so this is v0 squared over 2 sin 2 alpha. Okay, so d maximum of course occurs, d maximum when sin 2 alpha equal to 1, that gives you alpha pi over 4. Okay, now I want to using almost the similar situation, but what happen if we lift up the cannon a little bit? Yeah, like the cannon lie on the wall, right? So let's say we have those, and we have wall here, all right, and cannon is here. So that make angle, then we shoot that, so the profile is like that. Okay, and then it's given, so the question is, where does the projectile hit the ground, and with what speed? So basically we have, I can say extra when and where and with what speed. Okay, with given let's say this is 10 meter, those, let's say 10 meter, all right, this angle 45 degree or pi over 4. The initial velocity given v0, this is 150 meter per second. Okay, so that's all. I leave it this part to you as an exercise. put this in exercise. Okay. So with that example, and what I have explained to you today is the your normal plane, how to find the normal plane, how to find the osculating plane by knowing what is the tangent to a normal plane, what is tangent to the osculating plane. All right, I give you an example how to solve that problem, or how to find the equation of normal and osculating plane, as well as I end up with quite general application of vector on the projectile. Alright, this kind of problem actually, you can sit anywhere as long as you learn vector, not necessarily in this particular subject or in this particular topic. I mean, this particular chapter. No, you can during the vector, during the calculus, if you learn a vector a little bit, you can solve this problem. It's just a logic, and as well as how do you interpret or how do you write the coordinate x and y based on the given problem. Because remember that the position vector r is formed with that two component x and y. If you can find what x is, you can find what y is, then you should be able to solve this problem. So okay, with that I thank you. See you in the next video. Bye.